Hello everyone. Welcome to another Wave-to-Wave webinar as part of our series on automated fiber switching technology and deployments. We invite you to view our complete series of webinars to get the full overview of beneficial impacts automated fiber switching have in various deployment scenarios. Today's webinar will showcase ways mobile network operators, or MNOs, can achieve the benefits of decreased test and network provisioning times, faster time to revenue, better cash flow management, and deferred capital investments that are more aligned to 5G revenue streams. We will look at introducing automated fiber switching as an enabling ecosystem component for 5G wireless networks. Implementing reconfigurable solutions into 5G networks makes them scalable and modular, while ensuring MNOs are able to maximize their infrastructure return on investment as they adapt and evolve their networks for 5G deployments. Today's webinar will showcase the benefits of automated fiber switching technology in 5G deployments with a focus on front haul and back haul value propositions. Next slide, please. Today we'll start with the discussion on wireless network technology and market dynamics. Interestingly, we will demonstrate that fiber is a core technology that 5G will deploy to make the final wireless connection to the consumer successful. This is followed by a summary of 5G network architectures, and here we will also compare and contrast key differences with legacy wireless network architectures. We will then look at integrating automated fiber switching products and technology into 5G networks and their associated benefits. After that discussion, we will turn our attention to metropolitan networks and their role in 5G deployments. The packet-enhanced metro network can achieve not only service convergence and flexible service stand-ups with Layer 2 and Layer 3, but also large capacity and low latency service transport on Layer 0 and Layer 1. We'll round out the fiber discussion with a brief overview of 5G front haul, back haul fiber facilities testing. We will show that 5G OpEx savings can result from using an AFS as part of a testing approach. So let's get started. Next slide, please. There is no doubt 5G will soon be upon us as most major mobile network operators have already started deployments. Everyone from service providers to customers are excited about the potential of what 5G can bring to the table. For MNOs, the attraction is the ability to meet the increasingly high bandwidth demands from wireless customers. In a world that is dominated by the need to access high-quality video and applications from any device, anywhere, and anytime, MNOs are grasping at any solution that might provide a larger pipe for bandwidth and speed of service delivery. The exponential increase in mobile traffic over the past few years has been astounding, and this trend is still strong, with global mobile traffic expected to grow by a factor of 8x between 2015 and 2020, driven by new applications and use cases. They have attempted to keep up with market pressures by spectrum investments and deploying new generations of network technologies and architectures at an accelerated pace, from 2G to 3G to 4G LTE and now 5G. The only way the 5G revolution can proceed is if MNOs embrace the role of fiber. According to Cisco VNI report, mobile offload exceeded cellular traffic for the first time in 2015. Wireline fixed networks were utilized to handle nearly 51% of the total mobile data traffic, which works out to about 3.9 exabytes of data being offloaded onto the fixed wireline networks each month. 5G will need a robust wireline infrastructure to meet the expected amount of offloaded data from wireless network users. Next slide, please. Compared against 3G and 4G network architectures, 5G networks have a number of changes. For one, the core network deployment is virtualized. Through virtualization technology, physical entities of the core network are separated into multiple virtual network elements. In this way, their geographical positions are closer to radio terminals and latency can be reduced. There will also be more CRANs, and we invite you to view our M-Cord and wireless white papers and webinars for additional information on CRAN. Even in the 3G, 4G era, CRANs have demonstrated advantages in overall cost reduction, wireless collaborative anti-interference, energy savings, and operations and maintenance simplification. The CRAN architecture used in 5G facilitates flexible wireless resource management, allowing functions to be deployed flexibly to meet requirements of the mobile edge. It also supports hardware and software decoupling and enhances the software capabilities of wireless networks. Finally, the Mobile Switching Center, or MSC, the base station density is higher. 5G also uses a new spectrum. The 3.5 gigahertz and 6 gigahertz plus frequency bands are higher than the existing 3G, 4G frequency bands. Theoretically, the coverage range is smaller and more base stations are required. In hotspot areas with high capacity, ultra-dense base stations are used in networks, which moves fiber deeper into the network, and more transmission nodes are needed to be deployed. Next slide, please. Today, mobile radio stations are already connected with optical fiber along with directional radio and copper cables. Each of them have advantages and disadvantages. Current investments in fiber for mobile backhaul will continue as operators pre-build capacity in networks well in advance of 5G itself. Fiber and microwave will continue to have their places in modern 4G and 5G transport networks. In addition, densification means MNOs will be doubling down on their efforts to bring 5G technology to fruition even faster than originally anticipated. By solving the fiber challenge now, MNOs will be able to maintain a high quality of service for 5G networks as they are introduced and provide much needed network backbone expansion. Multi-tenancy in access and metro networks, such as with broadband competition, will also expedite fiber deployment as network operators search for business and market differentiators. Low latency targets for 5G leave little allowance for end-to-end delay, especially for rural deployments. Fiber is best suited to minimize that delay, but is also future-proof, as advances in optical spectral efficiency continue to expand its capacity and reach. Next slide, please. Let's take a look at the requirements placed by 5G on the connection of remote radio nodes and the expected cell concentration. A 5G backhaul network can be achieved through the collaboration between an IP network and a reconfigurable AFS optical network. IP routing and optical networks are the most basic infrastructure components of future 5G networks. The heavy IP traffic on routers that are directly connected through AFS optical layer channels reduce the number of intermediate routing hops and network latency, which improves throughput of routers. So ecosystem 5G network components can be broken into 4 prominent categories, as shown on the right-hand side of the slide. They are metropolitan backbone on-ramp components, wireless front haul network interface components, access network components, and network function virtualization components. The goal of these components is to not only replace legacy network elements with more agile and virtualized counterparts, but to also enable the network to quickly support more attractive and meaningful mobile services. This software-defined network approach integrated with an AFS can enable MNO business model transformation possibilities, such as base station virtual resource rental models or cellular infrastructure and intellectual property agencies, along with more premium mobile services. Next slide, please. The 5G ultimate vision is that of a flexible metro optical network capable of transparently interconnecting radio endpoints in the front hall, for example, a tower or a remote radio node, to the server or rack in the MSC where the BBU-DU is located. As shown here, the 5G network will not be based on one specific radio access technology. Instead, several 5G ecosystem vendors, including Wave2Wave, propose 5G as a flexible, adaptive portfolio platform of radio and fiber connectivity solutions. A 5G backhaul network will be achieved through the collaboration of IP and optical networks. IP and optical networks are the most basic infrastructure components of future 5G networks. In the architecture shown here, IP routers are directly connected through AFS switches to the metro network. As pointed out earlier, a mesh connectivity architecture reduces the number of intermediate routing hops and network latency, thereby improving the throughput of deployed routers. With an IP layer seamlessly integrated with an AFS-based reconfigurable fiber solution, the 5G's Layer 3 and Layer 2 network is maximized. Next slide, please. With wireless networks, available spectrum and spectral efficiency are flattening out. In fact, the spectral efficiency of 4G LTE PHY is fairly close to the Shannon capacity limit, and further improvements are likely very expensive to implement and will only provide limited gains. The surest way to increase per-user capacity is to make cells smaller and bring the base station logically closer to the mobile client. 5G implementation with centralized BBU-DU nodes provide on-demand allocation of computation processing resources. The Access Fiber Fronthaul Network, for example, a PON, connects the BBU-DU pool with geographically dispersed remote radio units. Information is exchanged between the RRU and the DU pool over the fronthaul access network. The goal of decoupling baseband processing from the remote radio units is to enhance redundancy and maximize operational reliability of the DU pool. The best facility for the fronthaul communications protocol CPRI link is dark fiber, because encapsulating CPRI into another protocol introduces too much latency and jitter to comply with the standard specification. If an area has limited fiber or rental wavelengths, passive optical networks, or PONs, are an excellent option. PON technologies create new possibilities for cost-effective convergence with 5G because a high number of CPRI signals can be transported into a smaller number of fiber cables using wavelengths and PONs instead of dedicated fiber links. Next slide, please. Metropolitan core networks are an integral part of the overall network hierarchy. Specifically, wireless 5G traffic within the metropolitan domain include remote radios, distributed antenna sites, and cell tower connectivity. As a result, metro core networks are characterized by a diverse base of protocols and backhaul fronthaul channel bandwidth. This ever-increasing traffic demand to, from, and between metro cells and DAS head ends are the primary driver of 5G traffic. The traffic demand is expected to accelerate with the coming introduction and adoption of consumer 4K and higher video content and services. The shift from data to video will add yet another set of bandwidth-intensive and latency-sensitive services to the mix. Also, fiber interconnects enable distributed antenna systems to be placed in the same room, floor, or building to form a DAS hub. In this way, 5G facilitates implementation of collaborative wireless radio networks to reduce interference and improve system performance. A fiber transport solution that supports streams between mobile switching center BBU-DU equipment and remote radio units while consuming few fiber resources is optimal. However, scaling to hundreds of fronthaul fiber links becomes an operational challenge without AFS components. AFS integration into the fronthaul termination deployment enables network reconfiguration economically, efficiently, and quickly. Next slide, please. To satisfy the stringent requirements of 5G, a metro optical network architecture is an ideal solution paradigm where computing resources are brought closer to the mobile user. The reduction in the average number of IP hops is achieved through widespread installation of mobile switching centers, re-architected into new M-Core data centers. These new MSCs will use content delivery networks that are based on advanced methods such as multi-protocol label switching to reduce the logical distance between traffic source and destination. Due to the rigidity and limitations imposed by conventional manual fiber patch panels, automated fiber switching becomes a key ecosystem component, especially when coupled with a router and a wavelength selective add-drop multiplexer. This results in a more flexible, automated metro optical network. A fiber management flexibility and reconfiguration point will coexist and can enhance both point-to-point and ring add-drop functionalities of optical transport devices and sophisticated routers. Mesh fiber layer designs coupled with routing mechanisms provide an elegant fit with Layer 3 protocols. It is a fact that mesh connectivity is more resource efficient for Layer 3 routing. Mesh networks require little upfront planning, allowing network operators to progressively grow their fiber network infrastructures as business demands arise, which is a realization of a pay-as-you-grow strategy. Next slide, please. Lastly, 5G OpEx savings can also result from testing multiple front-haul backhaul fiber links with the same OTDR by using an AFS to select the link to be tested. This approach enables a single OTDR to handle testing for an entire MSC. New fibers being installed can be connected to an OTDR or light source in the MSC. A technician arriving at the wireless tower, manhole, or cabinet where the fibers are terminated instructs the MSC NOC to connect the visible light source to a given target fiber, enabling the field tech to immediately identify the fiber. Cycling through this process allows the technician to complete the task quickly and accurately. The AFS may also be used to connect OTDR test equipment in order to characterize each newly installed fiber. When an outage does occur, the AFS enables remote troubleshooting by connecting the affected fiber to an OTDR to quickly locate the fault based on distance from the MSC. Technicians can then be efficiently dispatched directly to the location of the problem fiber. Next slide, please. So in summary, 5G requires increased network densification and greater deployment of fiber in the access network to support increased mobile backhaul and small cells. New video CDNs create tremendous opportunities for the mobile communications industry, but poses a strict challenge towards mobile communications technologies. Positioning AFS at critical points within 5G networks improve quality of service by offering a number of critical capabilities, including enabling a fast turnup of 5G infrastructure, fewer truck rolls to tower sites leading to direct labor savings, sharing of centrally located BBUs and test equipment such as OTDRs, and accurate connectivity records of remote cell sites. 5G also requires changes to legacy network infrastructure to deliver its promise. Mobile network operators must ensure they have the right tools for any front-haul, backhaul scenario. Fiber offers essentially unlimited capacity, security, reliability, and extremely low latency. And finally, an AFS integration provides added value of centralized testing that save many hours of windshield time to towers. So in closing, we want to thank you for joining us today, and we look forward to seeing you on another Wave to Wave